Hello, welcome back. This video we are going to model the inductance, and we really don't need to actually need to review on magnetic flux density and magnetic potential. If you are interested, you can give it a read. And what we are really interested is the lumped parameter model of the magnetic circuit. So I'm going to assume you know that we are using a lumped parameter model. That's much simpler and for analysis. And for our magnetic circuit, we basically have this law. So this is the Ohm's law for magnetic circuit. So the flux is equivalent to current in circuit. The MMF, magnetomotive force, F, is equivalent to the voltage in our circuit. And the magnetic conductance is equivalent to the inverse of our stator, the resistance in the circuit. Yeah, that's it. That's all you need to know. And also you need to know that the MMF here, F here is calculated by the turns times the turns number times the current. That's it. And if you know that, we are now ready to derive the expression for our inductance. So, so first we need to model our yeah, this is this is what we can derive if we know the definition for our flux linkages, the time integral of the back EMF. And we have this, and we plug in the result of Ohm's law for magnetic circuit here. So flux is equal to its source times the conductance, and we further plug in this the expression for MMF, and we realize that the inductance we have derived that it's partial derivative of flux linkage with respect to the current. So this is our very simple model for our inductance. So it's equal to the turns number squared times its conductance. However, in an electrical machine, this is not generally true because the magnetomotive force is not always equal to this turn number times current. So to be more specific, the turn number is not always zero along the air gap. We are going to model this function, which is the turn number as a function of the angular location along the air gap. And yeah, this is we can define the magnetic conductance of the air gap. Yeah, we are going to skip that. So in an electric machine, we need to reconsider this equation here. So the turn number here is now a function of theta. So yeah, so we can say that the winding is basically, or you can say the coils are distributed along the air gap. It's not it's a very simple model for a practical machine. And the current is a function of time. So our MMF here is actually a wave. You see, it's a wave. It's a function of time and the angular location. So it's a wave along the along the angular location over the rotor. So to derive an expression for our turn function and our MMF, we need to first consider a differential of conductance. It's corresponding to a differential of angular location in the air gap. Let me see if I have. Yeah, we are going to no, I don't have it. So basically, this is the differential. So we are going to consider, so this is the air gap. We are going to consider here, we do have some d alpha. So this is d alpha. So we have flux linkage here. These flux lines. So we are going to calculate the d phi that is accept in over this tiny space in our air gap. So it's basically it's calculated like like this. It has axial length of LE, and this is the radius, and this is the length of the air gap. So with all this is equal to the magnetic conductance in this tiny space. So the flux, according to Ohm's law for magnetic circuit, it's just like this. Yep. And to derive we are going to use this result to derive the winding function of inductance of the electrical machines. So to do that, we need to first have a model. So this is a very simple model. So we have stator iron and rotor iron, and we have some coils in the air gap, and we are going to apply the Ampere's law, Ampere's circuit law here. Let me see. It's what is the name of the law? Ampere's circuital law. And to apply this law, we need to have a closed loop, which contains a surface area of S. So in our case, we have 1, 2, 3, 4, these 4 points. We are going to have a circuit that goes through the air gap to in and out of the rotor and the stator. And yeah, we are going to apply the Ampere's circuit law over this closed circuit. So it's an integral over the magnetic intensity H, which is also a function of alpha. We are going to ignore that it's also a function of radial location R. We are going to assume the air gap is small enough. That's why it is only a function of alpha in our simple model. And this integral is equal to the integral of the current density over the surface area S. So basically, it's this current, right? This is the current, and this is equal to the current. So to do that, we are going to divide this path integral into 4 terms here. And we are going to assume the iron is ideal. There's no loss of MMF in the iron, so that's why we have 2, 0 here. So the path 2, 3, and path 4, 1, they are on the stator and rotor iron. And the MMF, we do have MMF loss in the air gap. That's why F12 and F34 is not 0. It's equal to magnetic intensity at angular location 0 degree times the length of the air gap. And also F34, so F34 is here, it's equal to the magnetic intensity at location alpha times the length of the air gap. Okay, so our objective is to derive the expression for H alpha here. And to do that, we need to first determine the value for H0 here. We are going to apply the Gauss's law for magnetism. So basically, the magnetic flux lines passing through a closed surface is 0. And with that, we will have so yeah. I'm not going to go through the details here. So basically, this gives us a result on a constant here that F34. If we integrate it over 0 to 2 pi, it's equal to 0. So that's why we can integrate equation 79 here. So this one, we are going to integrate this from 0 to 2 pi, and this term will be 0, and then we can derive an expression for H0. And yeah, that's it. That's how we did it. And note that this is the average value of the term function n alpha. So why we have term number here? It's because this is the current, and so we are going to assume the current passing through the coil, they are all equal to I, they are the same. And the number of current, then we can count for our current. So it's basically the turn number times the current, right? So N alpha is equal to, so because basically starting from here it's 0, it's count 1, and we don't count for other phase, I assume. So it's still 1, and from here, so this is negative turn. The current is flowing out of this paper. That's we are counting down. So counting 1 to 0 here, and 0, 0. So we have 1 turn from in this area, and the 0 term in this area. So our turn number, it should be 0.5, the average value for that. So this value should be 0.5. Okay. So so since we have this term value average, that's really dependent on where we start our integral. That's why we want to subtract this value from our term function, and like this. And this is known as the winding function of our coil, or of one phase. So it's independent on the where we start to do the integral or the counting. Yeah. Yep. That's winding function. We have derived winding function. So if you have winding function, if you time it with times, you multiply it with current, you have this MMF here. So in case your coil is moving somehow, your coil is moving in space, your winding function is also, so we can model that by this change of axis. So so that's how our winding function becomes a wave in the air gap, and the resulting MMF is also a wave in the air gap. And another example is that our winding function, an example of moving winding function is the magnetic field of the rotating PM. So in a practical motor, the engineers will make sure the MMF produced by the PM is sinusoidal as possible. That's why they are making this bread loaf look like shaped PM, and they just mount all those PM on a back iron as a rotor. So, and this is the expression for its MMF. Okay, so keep that in mind. We are now ready to derive the expression to calculate for mutual inductance. So mutual inductance is basically a result of some current in circuit A. The flux lines produced by the current IA is passes through the circuit, the space that it's passing through the coil of circuit B, and we have flux linkage on circuit B that's due to current IA. So basically we can do this using the term function or winding function by definition. So the flux linkage of circuit B due to current excitation on circuit A is equal to now, recall we do have derived the expression for our flux defined here. So we assume there's a flux linkage there's some flux in the air gap, and the turn number of our circuit B is NB at angular location alpha here. So the flux linkage is basically we integrate it over 0 to 2 pi. And so we plug in the expression for d phi, where this FA MMF of circuit A comes out. We just go through this derivation. Note that the average value can be removed because it's 0 when you integrate it over 0 to 2 pi, I assume. No. Oh, I see. So this is basically a sinusoidal function. So a sinusoidal function times a constant term here. It's 0 when you integrate it over 0 to 2 pi. So yeah, so you plug in this expression for NB here, so we reach out this result. So notice that FA is equal to NA times current. That's how we derive the expression for mutual inductance by taking time by dividing psi BA over IA. So mutual inductance is the integral of one function of circuit A and one function of circuit B. And note that we do have this associate law for our product operation. Multiplicate A. So we change the order of NA and NB does not really change the result of this integral. That's why we know that the mutual inductance LBA is actually equal to mutual inductance LAB. Okay, finally, we are now ready to derive the all of this mutual inductance between different phases and the PM. And here's the result. Basically, the flux linkage of circuit 1, 2, 3 due to PM is equal to some sinusoidal functions. There's a phase difference there. It's because the circuit 1, 2, 3 are placed at a different angular location along the air gap. They are like 120 degrees apart. Okay, so with this this expression for mutual inductance between the PM and the phase circuit available, we are now ready to derive the reaction torque example. So for example, consider the surface mounted PM synchronous machine above. So it's basically this rotor. Here is its torque. So it does not have, we assume it does not have reluctance torque, it does not have caulking torque, it only has this reaction torque. Now we have the expression for our mutual inductance between PM and phase circuit. We just plug in the expression. They are cosine, cosine, cosine. And here is our result. Yeah. So this sine, there's some trigonometry identities we can apply to simplify this expression. The sum of these three sine function that's evenly spaced in the air gap. It can be reduced to this result. I think I do have an appendix for that. Appendix. Yep. So this is from the book by Lipo and sine. So I think it's this one. We have sine squared term here. Let me see. We have sine. We don't have sine squared. Oh, I see. So we also need to plug in the expression for our current. So I1, I2, I3, they are also sinusoidal functions, such that we can apply this result or this result, such that all sinusoidal or sine or cosine, they are reduced to this constant value. We would like some to have some constant torque. That's why. So that's why we are going to. This motivates us that we want current to be sinusoidals, that with proper phase with respect to our rotor angular location and theta. That's why. So here is an example. I1, I2, I3, they are defined as this IQ amplitude times cosine of some synchronous angular speed of the current times t times some initial phase. So we are going to make this synchronous angular speed to be equal to the electrical angular location of the rotor. Yep, that's it. If you plug in this result we will reach to this result. So this is a constant torque, which is way better than our single phase ACPM motor example before. It has some fluctuation of some second order harmonic ripple in the torque expression. So this is a constant value. So all these, they are constant parameters, constant current amplitude, and we are going to pick a phi zero number that's maximizing our torque. So that's phi zero should be equal to pi over 2. Okay, so So one side note here is that when the current exists in the PM motor, it creates some kind of magnetic field. We know that. So the core energy is a function of the current. So that's why we know there's also magnetic energy in synchronous PM motor, which is making our motor has a reactive power to be less than to have reactive power, and its power factor is less than 1 for our PM motor. Yep. We are going to stop here. So for our next video, we are going to further to see how we can derive the result for induction machine.